Hi everyone, so in this video we are going to review your interim assessment number 1. So let's review some notes. Now this is way back at the beginning of the semester. So we did solving systems of equations. Now we looked at substitution, we looked at linear combination using multiplication and without, and we looked at graph or the Desmos. Now don't forget you can use Desmos. Desmos was that pretty cool graphing software that we used. So we know that if the two lines intersect, you are going to have one solution, and that solution is the point. So if the two lines intersect at one point, you have one solution, and your answer is the point that it intersects. Now, we had situations where we had no solution. And when you have no solution, those two lines are parallel. Okay, those two lines are parallel. And then we talked about infinitely many solutions. Now, when you have infinitely many solutions, that means those two lines are on top of each other. They are the same line. Okay, so those two lines are directly on top of each other. They are the same line. They coincide. So when that happens, you can have infinitely many solutions, because think about it, you can have an infinite amount of points where they intersect. You can have an infinite amount of points. We can draw points all the way up and down this line where they intersect. So you can have an infinite amount of points or solutions to that type of situation. And like I said, that's when they coincide. They're the same line. Next, we have the bounded intervals and unbounded intervals. So if you have a bounded interval, that means it goes between 2 points. So in this first example, we're looking at from 2 to 8. Now notice that your circles are colored in. Okay, if you have bounded inclusive interval, that means it includes those numbers, it includes those points. So it includes the 2 and it includes the 8. Because you have these equal signs, it includes it in your sign. So you have those colored in circles, solid circles. All right, next we have bounded exclusive interval. That means it does not include those 2 points. Oh, and also you have the interval notation, where if it includes the points, you have brackets. If it does not include it, or if it's exclusive, you have parentheses. So that's in the second example with parentheses. So we have from 2 to 8 with open circles, and it is bounded. Now you can have a bounded half-exclusive interval, going from 2 to 8, where it does not include the 2, but it does include the 8. So when you write your interval notation, you put a parentheses on the 2, bracket on the 8. All right, now let's talk about unbounded intervals. Okay, so we're looking over here at the unbounded intervals, where unbounded inclusive interval. So it's x is less than or equal to 8. So notice that's not bounded. It goes to negative infinity and beyond. So it goes from negative infinity to 8. And notice we put a bracket on the 8 because it includes it. It is inclusive, so it includes the 8. It can be equal to 8. And then if we look at this example right here, unbounded exclusive, so that is x is greater than 2. So notice there's no equal sign underneath it. It does not include the 2. So it does not include the 2, so we have an open circle, and it goes to positive infinity. So your interval notation goes from 2 to positive infinity. Also keep in mind, whenever you are writing your intervals or your intervals, you're going to use the words and or. Now, if it's a conjunction, that means it goes together. Typically, those are bounded. So you're going to use the word and. So here are some examples. It goes from 3 to 17. So that would look like, here's your 3, here's your 17. Let's just make sure. Now at 3 we have an open circle and it's all numbers greater than. And then at 17 I have another open circle, it's all numbers less than. So notice this is a bounded interval. So in your interval you should have a parentheses on the 17 because does not include the 17. Okay? And then if it's disjunction, which means here's your negative 2.5 and then here's your 5.8. So at negative 2.5 we have a colored in circle because you have the equal sign right there. And it's all numbers less than. And then at 5.8 we have an open circle because it does not include the 5.8 and it goes greater than. So notice disjunction use the word or because they are not connected. They are not bounded. And in your interval notation, you're going from negative infinity to negative 2.5, or anytime you see that U right there, that means or, from 5.8 with the parentheses to positive infinity. And then we have some more examples over here on the right. All right, and then next, we moved on to graphing in 2 dimensions. Remember that? It's pretty cool. We used Desmos. So closed half plane. So let's look at graphing this one. And also don't forget that if you have less than or less than or equal to, you shade below the line. Okay? And then if it's greater than or equal to, you shade it above the line. Now if it's just greater than or less than, it's a dashed line. That means it does not include where the line's at. And then if it's equal to, if you have the equal sign underneath it, it's a solid line. Okay, so these are important notes right here. I would suggest taking a screenshot of that right there just in case you need it. All right, so let's look over here on the graph. We have y is greater than or equal to 3/4 x minus 3. So that means we would put a point at -3 because that is your y-intercept. And then we would count our slope. So we would go up 3. So 1, 2, 3 over 4. 1, 2, 3, 4. That would be my next point. And then you would draw a solid line because you have an equal sign. See a little equal sign right there? You have an equal sign in your sign. So you would draw a solid line and it's greater than, so we would shade above the line. Okay? Or you can type this into Desmos and it gives you the graph. All right, so on this one, you're graphing 2 lines. Remember, we moved from 1 line and we went to 2 lines, and then we're going to get the solution set, which is where both of those lines intersect. So the place where both of those lines intersect is called the solution set. So notice we have both lines graphed, and the solution would be the shared shaded area. That's hard to say. And you can also type these into Desmos, and the darkest shaded area is your solution set. All right, next we talked about linear programming. So the point that maximizes or minimizes the objective function is usually one of the vertices. So in this example, we find the feasible region, which is where it is the shaded area in common, and that's that green area right here. You see that little green area? That is your feasible region. And then we take the points that make up the feasible region and we plug them into a table. We plug them into the objective function. So after you plug them into the objective function, you're going to get a minimum value and a maximum value. So depending on what the problem is asking for, if it's asking for the minimum value, then you would say you have a minimum of 14 at this point. Now if it's asking for the maximum, you would say we have a maximum of this value 40 at the point 211. And don't forget, you can also use factor trees. You can use the factoring trees when simplifying square roots or radicals. Okay, now you could also take this square root of 675 and figure out what perfect square goes into 675. Okay, you can also do that. If you have a calculator, if you have one of those TI-30, the XI, it's the blue and white one, you can, it will simplify these for you. So, if you take the square root of 675 and you can figure out that 15 squared goes into it, so that's 225. And we know that 675 divided by the The 225 gives you 3. So that means your 675 is made up of 225 times 3. Okay, I just wanted to make sure we show you both ways. So the square root of 225 is 15, and then you're left with the square root of 3. Okay, you can use whatever method you want. You can use the factoring tree, and that is here shown. Break it up into the factoring tree and then figure out how many pairs you have. You circle your pairs and bring those out. Or you can figure out what perfect square goes into that number. All right, then we moved into imaginary numbers. Now remember, I to the first through I to the fourth is very important. I would keep that somewhere. That's another one of those important things that I would take a screenshot of and keep it somewhere safe while you're taking your interim assessment. All right, imaginary numbers. We know that I is equal to the square root of -1. So we have to bring out that -1. And it becomes an I. So square root of -1 is I. And then we would simplify the square root of 200 by using your factoring trees or figure out what perfect square goes into it. Either way. But at the end, your answer would become 10I on the square root of 2. All right, then we talked about those complex numbers. Now, in complex numbers, the first number, the A number, is real. And the BI is an imaginary number. So you put them together and it makes it a complex number. Okay? So, for example, if you have 5 plus 2I, the real part is 5 and the imaginary part is 2. All right, so here's some examples here. Now, also look at this last example. You have a complex number of 17. Well, the real part is 17, and notice you don't have an I number. So your I number, your imaginary part, is 0. And then lastly, we took those complex numbers and we multiplied them. That was fun. So we multiplied them using your FOIL method, and this is right here. You're going to multiply them out. So you multiply your first one and the second one, you get all those 4 numbers. And don't forget, you have to change that I squared to -1. Remember that? I squared is equal to -1. Okay, that was very, very important. We know that I squared is equal to -1. That was super duper important right there. And then once we do that, we can simplify it down. And in this example, it's 42 plus 9i. So here are some practice problems. So let's work through these. Now, on the first one, use the graph shows the solution to which system of equations. Now, let's look at these 2 lines, and we need to figure out which one of these is it. Now, you can plug your answers into Desmos. I want to point that out. You can use Desmos, and you can plug them into Desmos. Okay, so I encourage you to check your work with Desmos. So you can do it by hand and then check your work with Desmos, or you can just use Desmos. It's completely up to you. Now, but I'm going to show you if you are on a test and maybe you don't have Desmos. Let's look at this first example. I know that this first line should have a y-intercept of 4. Okay, that should have a y-intercept of 4. Notice this blue line has a y-intercept of 2, and the other one has a y-intercept somewhere way down here in the negatives. So can't be that one. So using process of elimination, not A. All right, let's check out the next one. Now this next one has a y-intercept of -4. That could go through -4. What do you think? That could go through -4. Maybe. And -3x plus 2. Now this other one has a y-intercept of 2. That one could be. Okay. Could be, so I'm going to put a question mark beside it. It could be. It's not sure yet. Now let's check the other one. The other one has a y-intercept of -3. Well, that could go through -3, couldn't it? That could go through -3. And then the other one has a y-intercept of 3. Oh, look up here. This one has a y-intercept of 2, so it can't be that one. Can't be C. So that means my answer has to be B. Okay? And at this point, if you have Desmos, plug it in, or you can graph it. So you can graph your y-intercept and then count your slope. All right, over here on this one, we're going to do the same thing. We have to figure out which one of these equations is the equation of that line. So I'm going to find my y-intercept, and my y-intercept looks like 1, 2, 3. It is at 3. Okay, so my y-intercept is at 3. I can automatically eliminate C and D. Look at that. I've already narrowed it down to A and B. Now let's count the slope. Let's figure out where my next point is. Next point appears to be right there. So I'm going to go up 1, 2, 3, and over 2. So up 3 over 2. Up 3 over 2 is A for my slope, because remember, y equals mx plus b, where the m is the slope, b is your y-intercept. Okay? All right, so let's look at this one. Now, the system of inequalities is partially graphed. The only part that's missing is the shading. Man, missing the shading. So we need to figure out the shading. Which area of the diagram represents this shaded region? The shaded region that you would have in common, which would be the solution. So let's figure out, now I have this blue line. The blue line is the y is greater than or equal to x. So y is greater than or equal to x. Remember, greater than means I'm going to shade above. So here's that part. So I'm just shading above. Now let's talk about the green one. I want to color code. Here's green. So we have the y is less than or equal to -4. Less than means you shade below. So the region you have in common is this right here. Is this part right here at option D. So it'd be region D. Or area D. All right, so we have a couple more examples. Solve and graph this inequality. So we're going to solve it. So first thing we got to do, subtract 3. So I'm going to get -5x. I'm going to move that up here. So subtract 3. So that means I'm going to get -5x is greater than 15. Then we have to divide by the -5. Now, remember that important rule? Anytime you multiply or divide by a negative, that sign flips. So anytime you multiply or divide by a negative, the sign flips. I'm going to say it one more time. So anytime you multiply or divide by a negative, the sign flips. Okay? One more time. Anytime you multiply or divide by a negative, the sign flips. Okay, I think I've said it enough times that maybe it'll stick. So we have x is less than negative 3. Now we're going to put an open circle on negative 3. So that means it does not include negative 3 because we don't have that equal sign there. So we're going to go all numbers less than 3. Okay, solving graph. So this is our graph. Now, if I asked you to write this in interval notation, this is just a little side note. Okay, the interval would be from negative infinity to negative 3 with a parenthesis because it does not include the negative 3. If it includes it, you use a bracket. Okay, just a little side note because you will have some questions asking for the interval. All right, so let's look over here at this next problem. Identify the radical expression of 7 raised to the 1/3. All right, so 7, identify the radical expression. Okay, radical expression. That means you're going to have a radical. You're going to have a square root. Okay, so just knowing that alone, can't be A, can't be B. Okay, because that still has those fractions in the exponent. Don't want that. All right, so let's talk about 7 raised to the 1/3. Okay, that means I'm going to have 7 raised to the first with 3 as my index for the square root. So that just means I'm taking the third root of 7. Okay, so the bottom number of that exponent fraction becomes the number of the square root. That's the index of the square root. Okay. All right, so let's look at this one. Use the imaginary number I to rewrite the expression. Now, remember when we have that I, the negative underneath the square root, you have to bring that out. Okay, so this is just like you're taking negative 1, square root of negative 1 times square root of 81. So the square root of negative 1 is I. The square root of 81 is 9. But when we write our imaginary number, we usually write the number first and then the letter. So that becomes 9i as our answer. Now over here we're simplifying these square roots. So we have to simplify the square roots first. So in the first one, what perfect square goes into 20? Perfect square goes into 20. That becomes a 4 times the 5 plus 4. Now we need to figure out what perfect square goes into 45. Well, that is 9 times 5 plus the square root of 5. All right, square root of 4 gives me a 2 on the square root of 5 plus 4 times 3 because the square root of 9 is 3. And you leave that square root of 5 plus the square root of 5. All right, so now we need to take that 4 times 3. So I have 2, the square root of 5 plus 12, because 4 times 3 is 12, and the square root of 5 plus square root of 5. Now, when you are adding or subtracting square root numbers, it's just like you're adding and subtracting variables. You have to have the same square root, and you have to have the same numbers underneath the square root. So let's check that. And notice that we have square root of 5s on all of them, so we can combine them. So we're going to have square root of 5, and we get 2 plus 12 plus 1. So that gives me 15 on the square root of 5 as your answer. So 15 on the square root of 5 is your answer for this one. All right, so in our next example, we are going to multiply and simplify. So we are going to use our FOIL methods. We have 3 times 5, that is 15. And then we have our 3 times negative 4i, so that is negative 12i. Then we have 2i times 5, that is plus 10i. Then we have 2i times negative 4i, so that is negative 8i squared. So next, combine your like terms. So we get a negative 2i in the middle bring down your 15. And then you have this minus 8. And don't forget, I squared changes to negative 1. I'm going to write it up here. I squared is equal to negative 1. Very important here. So that means we have negative 8 times negative 1. That gives me a plus 8. Bring down your 15 minus 2i. So combine your 15 and your 8, and you're going to get a 23 minus 2i. And then over here, you're going to simplify. So we have the square root of 24. So you need to figure out what perfect square goes into 24. Well, that is 4 times 6. And then we have the x to the 10th, y to the 5th, and z squared. All right, so I'm going to bring out that square root of 4. So that is a 2. Leave some space. Now let's talk about x to the 10th. Now, how many pairs of x's do you have in x to the 10th? Well, you have 5 pairs. So that means you're going to bring out x to the 5th. And there's none left over. Now, when you have y to the 5th, how many pairs of y's do you have? Which means how many times can you divide that by 2? Well, that means you're going to have y to the 2nd power because you have 2 pairs of y's and y to the 5th with 1 y left over. And then next you have z squared. So how many pairs do you have in z squared? Well, that is 1 pair of z's. So you bring out that 1z. So your answer is 2x to the 5th, y squared, z, on the square root of 6y. So I'm going to write that a little better. Y squared, and then you have a z, square root of 6y. It's the same thing, I just rewrote it so it's a little better looking. All right, so next we're going to identify the rational exponential expression of the cubed root of 11. So notice 11 will have a power of 1. So that means we take that 11 to the first power and divide that first power to the third. So that means we have 11 to the 1/3 is how you would rewrite this in rational exponential expression form. Next, we're going to use the imaginary number to rewrite the expression as a complex number. So first we have the square root of 25, that is 5, plus, so we have the square root of negative 36. So we know we need that I. Then you can take the square root of 36, and the square root of 36 is 6. So we have 5 plus 6i as our answer. Next, we're going to simplify. Now notice you can only add or subtract like terms. So our like terms here would be the I numbers. We have 5i plus 11i. That gives me 18 plus, now that 5i plus 11i gives me 16i. So 18 plus 16i is choice B. All right. Next, we have I to the 19th. Now remember that I to the 4th is equal to 1. Okay, a couple slides, you can go back a couple of slides, and you're going to find that table of I to the 1st, I 2nd, I 3rd, and I 4th. Actually, I'll go ahead and write them here. So I is equal to I, or the square root of I squared is negative 1. I to the 3rd power is negative I. Okay, so I to the 19th. We're going to figure out how many times does 4 go into 19. So we're going to get our handy dandy calculators. We're going to take 19 divided by 4, and you get 4.75. So that means I have I to the 4th raised to the 4th power. Now what is that? 16. So that gives me I to the 16. How many was left over? 3. So I have that I to the 4th raised to the 4th power, because that 4 times 4 gives you that 16 times I to the 3rd. Now, why do we want to use I to the 4th? Well, because I to the 4th is 1. 1 raised to any power is 1. So that means we're left with I to the third. Okay, now I to the third, we said, is -1, or a negative I. So that means we're left with negative I as our answer. So that's why that I to the fourth table is so important when you are reducing these. We're left with I to the third, so that gives me negative I, which is answer A.